All right, so in this video, we're going to talk about the multivariable chain rule. Before we get into the multivariable chain rule, I think it's important to point out and remind you of the chain rule from Calc 1. So if I let y equal f of x and x equal g of t, then we've defined dy dt to be dy dx times dx dt. So that's Calc 1. Now, one of the things I'm going to show you here for this particular chain rule is going to be almost ridiculously unnecessary at this point, but it's very important to use it moving forward. What's happening here is we're actually starting with y. And from here, we're moving into x's, and from here, we're moving into t's. Now, again, that's important to understand, not so much now as it is going to be here in a few minutes. But essentially what's happening is you're starting with a function with respect to x, so y goes to x, but then our x goes to t, so our x goes to t. And the dy dx is represented by this arrow right here, and the dx dt is represented by this single arrow right here. All right, so again, doesn't make a whole lot of sense as to why that would be important for this particular case, but if you sit tight in just a second, you'll see where it's going to grow into. So let's go ahead and take a look at now, I'll say consider z equals f of xy, where x equals x of t and y equals y of t. If we want to find dz dt, all right, dz dt, what's happening is our z is a function of x and y, where x is a function of t and y is a function of t. So let me go ahead and construct a diagram for this one similar to what I did here. So we know that z is going to be a function of both x and y. So it could be a function of x, it could be a function of y. We also know that x is a function of t and y is a function of t. So we're going to have branches coming out of both of those into t's. Now, if our job is to come up with dz dt, we're going to have to use all pathways leading us there. So to do this, I'm going to start with my first pathway. Notice here how you're leaving z and going to either an x or a y. That means you have choices. If you have more than one arrow coming out, it's got to be a partial derivative. So I'm going to have partial z, partial x. So partial z, partial x. Partial z, partial x got me to here. Now there's only one pathway leading me to this t. So that's going to be a Calc 1 single variable derivative, dx dt. So dx dt. So partial derivative of z with respect to x, derivative of x with respect to t. Now we have another option. So we're going to do a plus partial z partial y, partial z partial y, times only one route, so now it's a Calc 1 single variable derivative, dy dt. So dy dt. So that's how you would come up with the partial derivative, or not the partial, the derivative of z with respect to t by following this format. So the reason I thought it was important to show up here is to emphasize what these mappings or what these arrows that truly stood for. And you can see there's only one arrow coming out of y, there's only one arrow coming out of x, that's why we have the Calc 1 derivative. Now that there's two possible options, and that's where the partial derivative is going to have to come into play. All right, so let me go ahead and leave this up on the screen, but slide it up. Let me go ahead now and consider z, or let me call it w, equals f of xyz, where x equals x of t, y equals y of t, and z equals z of t. Let's suppose now we want dw dt. So let's set up a similar diagram. We know that w is going to go to either x, y, or z. W is a function of x, y, and z. X is going to go to t, y is going to go to t, z is going to go to t. So we're going to have a t, and a t. All right, so for the first part, it's going to be partial w, partial x. Because there were multiple branches coming out, it's going to have to be a partial derivative. But now that we're here, it's going to be a Calc 1 derivative because it's only a single variable mapping. So that's going to be dx dt plus partial w partial y dy dt plus partial w partial z dz dt. So for these, I went a little faster through the partial w partial y. Since there's multiple options, we're now picking this path. Then it's a single variable dy dt plus partial w partial z, and then a single variable dz dt. So this would be the format to find dw dt given these conditions here. All right, now let's take a look at an example using that. So I've just come up with my format for dw dt given those conditions. Let me go ahead and use as an example now w equaling the square root of 1 plus x minus 2 xy z to the fourth, where x is equal to the natural log of t, y is equal to t, and z is equal to 4t. So you can see we've got w as a function of x, y, and z. X is a function of t, y is a function of t, z is a function of t. So all we need to do now to find dw dt is to run through this right here. So dw dt. The first part is going to be the partial of w with respect to x. So the partial of w with respect to x. Now remember, for with respect to x, that means y's and z's are constants. So to get things started there, I'm going to have the 1/2, keep the inside the same, subtract 1, back times the derivative of the inside with respect to x, this guy right here, with respect to x. And that inside then is going to turn into 1 minus 2y z to the fourth. So again, this is the derivative of the inside here with respect to x. Now we need times derivative of x with respect to t. Well, that's just going to be a 1 over t. So times 1 over t. Now, we've got a plus, and for screen purposes, I'm going to put it underneath here. So that's going to be a plus. Now we'll need the partial of w with respect to y. So partial of this guy with respect to y. So similar chain rule, 1/2, keep the inside the same, subtract 1, and then the derivative of the inside here with respect to y, and that's going to give us a negative 2x z to the fourth, and then times the derivative of y with respect to t, which would just be a 1. Finally, that plus right there is going to be this plus here, partial of w with respect to z. So we've got our 1/2, keep the inside the same, subtract 1. Now, derivative of the inside here with respect to z. So that's going to give us a negative 8xyz cubed. And then finally, derivative of z with respect to t, which would be 4. So it's a pretty nasty looking derivative, but when you think about it, so is the function. If I take x as natural log of t and I plug it in there and there, if I take y as t and plug it in there, if I take z as 4t and plug it in there, this is going to create a pretty big mess, which if I wanted to then directly take the derivative of w with respect to t, you would in fact end up with all of this.